The Arctic's climate change challenge, understanding permafrost and carbon dynamics. The Arctic is experiencing a warming trend that is twice the global average, leading to significant environmental changes, particularly in permafrost regions. This warming has critical implications for carbon storage and greenhouse gas emissions, which are central to understanding climate change dynamics. The importance of permafrost. Permafrost, a layer of permanently frozen soil, contains vast amounts of organic carbon, estimated between 1,460 and 1,600 petagrams. This carbon is primarily found in the upper 3 meters of soil and has been preserved since the last ice age. As the Arctic warms, permafrost thaws, releasing carbon dioxide and methane into the atmosphere. This release poses a significant risk for accelerated climate change, as these greenhouse gases contribute to global warming. Carbon storage and release mechanisms. Carbon reservoirs, a substantial portion of carbon, about 25 to 30%, is stored deep in permafrost soils, particularly in the Yadoma regions of Siberia and Alaska. These deposits can be tens of meters thick and hold between 327 and 466 pgc. Thawing dynamics. Thawing can occur gradually or suddenly, leading to the formation of thermokarst lakes, which further complicate carbon accumulation and storage. As the climate warms, the balance between carbon uptake by plant growth and carbon release through respiration and decomposition shifts, raising questions about whether the Arctic acts as a net carbon source or sink. Ecosystem responses and carbon balance. The carbon dynamics in Arctic ecosystems are influenced by seasonal changes in ecosystem types. During the brief summer growing season, northern tundra and boreal ecosystems typically function as carbon sinks, absorbing more carbon through photosynthesis than they release. However, during the fall, winter, and spring, carbon losses can offset summer gains due to microbial activity in dormant plants. Ecosystem variability. Different ecosystems respond uniquely to climate change. For instance, wetlands often act as net carbon sinks despite releasing methane, while tundra regions have shown a tendency to release carbon. Measurement challenges. Accurately assessing the overall carbon balance in the Arctic is complicated by the scarcity of measurement sites and the variability in carbon fluxes across different types of ecosystems. Recent findings on carbon fluxes. Recent studies have sought to synthesize data on carbon exchange in Arctic ecosystems, focusing on CO2 flux measurements. Notable findings include tundra and boreal forest dynamics. A study found that between 2012 and 2014, the tundra region in Alaska was a consistent source of CO2, while boreal forest exhibited more variability, sometimes functioning as a carbon sink. Regional carbon source estimate. The average net carbon source for the Alaska study area was estimated at 0.02, 5.01 for pgc per year, which, when scaled to the entire northern circumpolar permafrost region, suggests a net source of approximately 0.3 pgc per year. Long-term trends. Historically, the Arctic has functioned as a net sink for atmospheric carbon dioxide, but recent data indicates a potential shift, suggesting that the cumulative effects of terrestrial ecosystems may now be exacerbating climate change rather than mitigating it. Winter carbon flux and its implications. A significant aspect of carbon dynamics in the Arctic is the role of winter carbon fluxes. Recent synthesis studies indicate that carbon emissions during the winter months may be 2 to 3 times greater than previously estimated. This has critical implications for understanding the annual carbon balance. Winter emissions. The winter carbon release may offset the carbon absorbed during the summer, leading to an estimated total release of 0.6 pgc per year in the circumpolar region. Feedback mechanisms. These findings support the notion that feedback loops from changing permafrost ecosystems could already be impacting climate change, highlighting the urgency of addressing these changes. Technological advances in measurement. Recent atmospheric measurement campaigns, particularly those conducted by NASA, have provided valuable insights into greenhouse gas concentrations over the Arctic. These campaigns have improved our understanding of how changing ecosystems affect atmospheric greenhouse gas levels. Aircraft measurements. NASA's aircraft measurements over Alaska from 2012 to 2014 allowed researchers to assess the impact of tundra, boreal forests, and wetland ecosystems on atmospheric carbon levels. Seasonal limitations, however. The long, cold winters in the Arctic pose challenges for measurement, as many observations are limited to the warmer months. Conclusion. The interplay between warming temperatures, permafrost thawing, and carbon dynamics in the Arctic presents a complex challenge for climate science. As the region transitions from a carbon sink to a potential carbon source, understanding these processes is crucial for predicting future climate scenarios. Ongoing research and improved measurement techniques will be essential in addressing the significant implications of these changes for global climate patterns.